Leetcode problem 307, read some query mutable. So the problem is that we are given an array, for example 1, 3, and 5, and this array is mutable. So for the because there is update. So for example, we can't calculate the read sum if there's no update. So we can use the prefix sum. But if there's update, we have to use another data structure, maybe binary index tree or maybe segment tree. But for this video, I'm gonna introduce a binary index tree. So for example, we have a number 135, and we want to calculate the sum reads from 0 to 2, so it's gonna be 9. And then we want to update it for index 1, we're gonna update it to 2, so the result is gonna be 8. So this is the dynamic update for a number, and then we're gonna continue to calculate the range sum. So let me talk about where the template is. Yeah, you can check my GitHub. So normally I prepared what is a binary index tree, and you can also check this video. And from the stable sort, this video about family tree, it has given a very detailed explanation of what is a binary index tree. Yeah, and you can check the Java source code. But for me, I prefer to use Python. So yeah, let me just turn to my template. Yeah, let me just copy the template and explain it, and then I'm gonna use the template directly to solve the problem. Yeah. So for the template, I checked the reference video. Basically, there are 3 operations we need to take care. So one is add, another is the sum, and the last one is the initialization for the self.tree for this array. Yeah. So the sum operation is that while we are calculating a number, so for example sum 7, so this means from index 1 to index 7, so we're gonna calculate it. So while we are going to calculate it, we're going to use the low bit operation. So the low bit operation is this number. Yeah, so this number I and minus I. So this is going to be the low bit operation. So in my template, I'm going to use a low bit to represent the index I and minus I. So for example, for this 7, so the bit is 00111. So we are going to check the low bit of this 7. So what is the low bit? It is this one. Yeah. So this I is 7. So minus the low bit is 1. So it's gonna be 6. So first of all, so this 7 gonna be first of all it's gonna be this array T7 plus T6, and 6 is 110. We are going to check the low bit, and the low bit is 2. So it means 110 minus the low bit 10, it is 2. This is the binary representation, so it's going to be 100, it's going to be 4. So this is going to be the last one, so 10 and 0. Now we are going to check the low bit. So the low bit is this one, and yeah, the low bit is this one, and our I is also this 4. So 4 minus 4, 100, so it's gonna become 0. So if I equal to 0, it will go out of the while loop, and we're gonna return the sum directly. Yeah, so this is why it comes to 4, and for the next one, the I gonna become 0. Yeah, because 7 gonna update it to 6, and 6 gonna update it to 4, and for I equal to 4, so 4 minus 4, it's gonna become 0. Yeah. And about the low bit operation, it is here. So for example, 7 and minus 7, we use the 2's complement. So 2's complement of 7. So for calculating minus 7, the bit representation, it is the 2's complement. So 2's complement plus 1. So for this number, we're gonna check 7, so 2's complement is 1100, and then we're gonna plus 1, so 11001. So it is this number and this number, it's gonna become 1, as you can see, and this is exactly the low bit of 111. Yeah, so actually this is just the low bit operation. And another one is the add operation. So the add operation is that we are going to add a number to the index 4. So for example, this is index 4. We are going to add a number to this index 4, and how we're gonna add it? So first of all, before that, this number is 13. Yeah. So it's gonna be 13 plus 10. It's gonna be 23. So after calculating that, we're gonna use the low bit operation again, but this is gonna be plus. So for example, 4 plus equal to the low bit operation, and it's gonna be 4. Yeah. So it's gonna be 8, and so for the T8, it's gonna be updated to 41 plus 10. Before that, it is 41 plus 10. It is 51. And then we're gonna continue the low bit operation, and it's gonna be 1, 0, 0, 0, and 0. It's gonna be 16. 16 will go out of the range of the array because the length, the last index of the array is 15. But currently we have 16. It is more than that. Yeah. So if I is less than the array.length, it is okay. But if it is more than and equal, because the I equal to 16, the array's length is also 16. It is more than and equal, so we're gonna go out of the while loop, and we're gonna finish the add operation. Yeah. So basically, those two operations are most important for us. One is sum, and one is add. Yeah. Another one is just make. So the make is just a preparation. It is the initialization in my template. So the initialization is that we're gonna use a for loop to prepare all those numbers. For example, if the low bit, for example, for the first position, the bit is 1, we're gonna keep the numbers as 5. This is 1, we're gonna keep 9. But for the second one, if this is a 1 for the second bit from the right to the left. So if it is 1, we're gonna sum up from the first one because this is his parent. So this P is the parent of this I. So it's gonna be 5 plus 2 gonna become 7. And what is the parent of this? And the 4 and this number is the parent of this one and this one. Yeah, so this means this number gonna plus this one and plus 1. It's gonna become 4. Yeah, so it's gonna be I don't know why it is calculated like that, but it should be okay. Let's just use another example maybe. So for example, this number, let's use this example. This is 13. So how can we get 13? So this is 7 because this is 1. Its parent is 2. Yeah, its parent is 2, and this is 9. And for this number, it's gonna be this number gonna be it's gonna be 7 plus 9. It's gonna be 16, and plus this minus 3. It's gonna be 13. Yeah. So this is they used the make. It is the initialization of the array. Basically, this P is just needed to find the parent. So for example, for the index 1, index 1's parent is index 2 because 1 is 0, 1. Its parent is 1, 0. Yeah, so it is 2. But what about index 2's parent? Index 2's parent, according to the operation, I plus the low bit, it's going to be 4. So 2's parent is going to be 4. So what is the index 3's parent? It is also 4. Yeah, because this is 3 plus the low bit is 3, the low bit is 1, so it is also 4. Yeah. So in this way, we only used on time to get a self-tree with this array, and then we're going to use this array to finish all the add sum operation. Yeah. Now I'm going to use my template to solve the problem. So let me just copy the template from here and explain why we can use it directly. Let me first explain about this kind of template. So the self.tree, we are going to calculate it from index 1 to index n. This index 0 it is just a dummy position. This will not take part into the calculation. Because this kind of design is very useful for us to write the code very clean. Yeah. So we will not use the index 0, we're going to use the index 1 to n. And similarly for here, I prepared the self.n equal to the length of self.train. Self.train is just a binary index tree array because we're going to use this array. And we're going to initialize the array and sum up the values to it. So for I in range from the second one, from the index 1. Yeah, because we are not considering this index 0. So from 1 to self.n, and we're going to prepare the parent. So the parent should equal to I plus the low bit, self.low bit. So I prepared a low bit from here. And if this parent is less than the length of the array self.n, it means we're gonna plus the value to its parent. So self.tree.parent should plus equal to self.tree_i, this value. And this is just a low bit. And then we're gonna focus on the add and the sum operation, because the update and query is just we used the sum, and for this update we just use the add and the query. Yeah, so we just need to understand what is add and what is the sum. So the add is just add a value to index I. So at index I, we're going to add a value. Also, we're going to check the range. If it is less than the length of the array, self.n, so we're going to update the value self.tree_i should plus equal to this number k. And then we're going to update it to all other positions. We're going to update it. So we're going to use I plus equal to self.low bit. So for example, if this number, so for example, if it is 4, we're going to update it to 4 plus the low bit, it's going to be 8, 8 plus the low bit, it's going to be 16, it's going to be 32. Yeah, so it's going to be something like this. So this is why we can calculate it in log n time for the AND operation. And also here for the sum operation. So the sum is just the operator. So for this, we're going to prepare a result and return this result. Yeah, we're going to check the index. If this index is more than 0, why are we going to check the index more than 0? Because the index is going to become smaller and smaller. And we're going to use the result plus equal to the self.tree_i at the current position. And then we're going to use the low bit operation. So I should minus equal to this value. So for example, we have number 7. It is 111. Next, it's going to become 7 plus minus the low bit. It's going to be 110. It's going to become 6. And then the next low bit is going to be 100. It's going to be 4. So it means it's going to be self.tree plus self.tree7 plus self.tree6 plus self.tree4. This is exactly like the example. And then we just need to return the sum of them, the result. Yeah. Now, if we understand all about that, so this query and update is just useful for the query and update operation, because a lot of problems actually they didn't ask you the sum, because sum is from index 1 to index from index 0 to index I. Yeah, but for most of the problem they just ask you yeah, for our problem, normally they ask you from the index 0 to index I. But for the sum, for the binary index tree, this sum is from index 1 to index n, because this is according to the design of the problem. This is going to be much easier to write the code. And for the query, yeah, let's understand the query first. So the query is just query from the L to R index inclusive. As the sum is defined from index 1. So here we're gonna change a little bit. It's gonna be R plus 1 to L. Normally it should be sum R minus L minus 1, but the index is coming from 1, not 0. So we're gonna plus a 1, and here also plus 1. It's gonna become index L, and here gonna become R plus 1. And for the updates, normally we can get a value by using the self.query I. It means the at index I we're gonna get the count value. And because we want to update, but currently we only have the AND function, so we're going to use the AND. So if we want to update a value, so for example from 3 we want to update it to 4, So what's gonna happen? Yeah, currently we can get this current value. It is 3. Yeah, and actually this value is just 1. 3 updated to 4, it means we're gonna add 1. So it means this value k is 4. 4 minus the current value 3. It means add 1. So we're gonna add 1. But the position should be I plus 1 because yeah, we prepared the index from 1 to n, not 0 to n minus 1. So this is why we're gonna use I plus 1 to add the value. Why we are using the add, it is I plus 1. Yeah. But while we are using query, we've already changed it. We can directly use I to I. Let me check if there's anything else to understand. Yeah. Normally for this and, this I cannot equal to 0. Because if it is equal to 0, it's going to be an infinite loop. Yeah. So this is why while we are going to use some add operations, even yeah, while we are using some update operations, even there is a 0 inside, but it is okay because for our add we're gonna plus a 1. If we plus a 1, normally this I can never become 0. This is why there's no infinite loop for this kind of template. Yeah. If we understand the template, I think now we can just finish the coding because this is just a template question. If we are familiar with the template, normally we can use it to solve the problem. So we're gonna prepare a self.tree to be equal to binary index tree, and we're gonna just put the nums inside. And here for the update, we just need to update the value. It's gonna be self.tree.update with the index to this value. And finally, it's gonna be the so here about this kind of code, it is dependent on the template. So if you write a complicated template, not complicated, if you write a lot of operations for your template, normally you can save the lines of code from here because you prepared the update, you prepared the query, so you can use it directly. So self.tree and .query, you can use it directly with left to right. So this is going to be the code. I think the difficult part is you need to understand the template. It is a lot of code from beginning. You don't need to remember each of the line, but you need to understand all the operations about it and try to use it to solve problems. And after solving maybe a lot of problems, then maybe you're gonna try to remember how to write the template by yourself. Now let me run it to check. There's something wrong. I hope I didn't copy. Here I didn't return. I need to return a number for the summaries, and for the update I don't need to return. Now let me submit it to prove this template is right. As you can see, it passed and it is okay. And basically for this question, you can check the template. So from my GitHub, to check the patterns, inside the patterns there's a binary index tree. You can try to copy the code and try to understand the template. Or you can just check it from the template. Inside the template, I think there is also binary index tree. And basically I prepared the template. I prepared for questions. You can check it one by one and to just get familiar with what is a binary index tree and why you can use it to solve a lot of problems like updating a value, the summaries of a value. Thank you for watching. See you next time.